complex numbers, equality in complex numbers. So in this topic, what we're going to be looking at is where we're given some sort of a statement where the left-hand side is equal to the right-hand side, and we're going to have unknown values in it which we have to solve. For example, x plus yi equals 2 minus 3i times 3 plus I, and we want to find the value of x and y. So what this means is that everything on the left is equal to everything on the right-hand side. But of course, we are going to have to get rid of these brackets on the right-hand side first, so we can look at how can we figure out what x and y are. So if I multiply out the brackets on the right-hand side, I have 2 times 3 is 6, 2 times I minus 3i times 3, and minus 3i times I is minus 3i squared. And of course, we remember that I squared equals minus 1. So then that's going to simplify the right-hand side to 6 minus 7i, and then minus 3 times minus 1 is plus 3. So that means that x plus yi equals 9 minus 7i. So this is a very easy question now, because I can see that if I compare left with right, well, x is the real part of my complex number, y is the imaginary part, and on the right-hand side, 9 is the real part, and minus 7 is the imaginary part. So by equating the left-hand side with the right-hand side, we now can solve for x and y. So in other words, x on the left has to equal 9 on the right, and y on the left has to equal minus 7 on the right. So with the imaginary parts, we're always looking at the coefficient of I. We do not need to put any i's in the answer, because it's the coefficient of I on the left must equal the coefficient of I on the right. So let's take a second example. So we have x plus yi plus y minus xi equals 10 minus 2i. So here I can't add any of these terms on the left, and obviously on the right-hand side we only have two terms, 10 and minus 2i. So again, what we do is we underline our real and our imaginary parts on both the left and on the right-hand side. And then what we do is we say, well, everything on the left must equal everything on the right. So we equate the real parts on the left with the real parts on the right, and the imaginary parts on the left with the imaginary parts on the right. So all the real parts on the left are x plus y, and all the real parts on the right are 10. So we get an equation, x plus y equals 10. And then if we look at the coefficients of the imaginary parts on the left, we have y minus x must equal the imaginary parts on the right, which is minus 2, which gives me a second equation. So of course we can see here that this is going to end up with simultaneous equations. So if I line up the x's and I line up the y's, well, this is a nice straightforward simultaneous equation, because the x's are the same coefficient but opposite sign, so that cancels straight away. And y plus y is 2y, 10 minus 2 is 8, therefore the value of y has to be 8 divided by 2, which is 4. And then to solve for x, we simply just take y, and we're going to sub y into either equation 1 or 2. I'm going to go with 1. And that gives me x plus 4 equals 10. Therefore, x equals 10 minus 4, which is 6. So in general, we start by expanding and simplifying any brackets, underlining all the real and the imaginary parts on both sides of the equation, taking the real parts on the left and equating them to the real parts on the right, and then doing the same for the imaginary parts. So the imaginary parts on the left equal the imaginary parts on the right. And then if we end up with a simultaneous equation, we simply solve our simultaneous equation. Or if we have something nice like the first example, we can often end up with the answer straight away. So one more example, slightly different version of this, is where we're given express the square root of 3 plus 4i in the form of a plus bi. So what we do is we let the square root of 3 plus 4i equal a plus bi, and what we want to do is solve for the value of a and b. So because this is a square root on the left, what we're going to have to do is square both sides to get rid of that square root sign. So of course be very careful when squaring out the right hand side. It's a plus bi times a plus bi. So on the left, if I square the brackets, I get 3 plus 4i. And on the right hand side, if I square a plus bi, well, I square the first, multiply them and double it, and square the second term. And of course, remembering that I squared equals minus 1. So that gives me 3 plus 4i equals a squared plus 2abi minus b squared. So underlining the real parts and the imaginary parts on the left and on the right. And then we equate the left-hand side with the right-hand side. So the real on the left is 3, and the real on the right is a squared minus b squared. And on the imaginary parts then, on the left we have 4, and on the right hand side we have 2ab. So that can simplify to give me 2 equals ab. So this simultaneous equation is obviously a non-linear simultaneous equation. So that means I'm going to have to take one and write it in terms of the other. So I'm going to take the letter a, and if I divide both sides by b, that gives me a is equal to 2b. I'm now going to sub a into the first equation. So we said a was 2 over b. So that's going to be a squared minus b squared. So squaring out the brackets there, that gives me 4 over b squared minus b squared. And if I multiply everything across by b squared, I can get rid of my fraction. So b squared times 4 over b squared just gives me 4. And b squared by minus b squared gives me minus b to the power of 4. Now, if I bring everything to one side, we should see that this actually resembles a quadratic equation. So if I look at the last term there, what multiplies to give me minus 4, that adds to give me 3. It must be 4 and minus 1. So if I sub back in, instead of 3b squared, I have 4b squared minus b squared minus 4. So grouping the first two, grouping the second two, and taking out my highest common factor, I have b squared is common to the first two terms, leaving me with b squared plus 4. And minus 1 is common, leaving me with b squared plus 4. And of course, these two brackets always have to be the same when we're factorising our quadratics, so that I can take that out as the highest common factor, which then leaves me with b squared minus 1 equals 0. So if I take both of my factors and I let them equal 0, I can then solve for b. However, if we look at the first one, b squared equals minus 4, well, I can't solve that because that would give me the square root of minus 4. And of course, a and b are always elements of the real numbers, because remember that the complex number is z is equal to a plus bi. So of course, a is real number and b is a real number, which is the imaginary part of the complex number. So I can't have b is equal to some sort of an I when there's already an I there. And if I look at the second equation, well, I get b squared is equal to 1. And if I get the square root of 1, well, we have to remember that the answer is plus or minus 1. So if b is plus or minus 1 and a is equal to 2 over b, well then if a is going to be 2 divided by 1, in other words, a is 2. And when b is minus 1, well, that gives me a is equal to 2 divided by minus 1, so a is minus 2. So therefore, the square root of 3 plus 4i can be written as 2 plus I, or minus 2 minus I. So if you then answer all the questions on your equality sheet.